Today, we're going to take a look at some of the physics of stationary waves. We'll start with a slinky. In order to achieve this stationary wave, I sent out a wave from my side of the slinky. Let's call that wave the Jedi wave. Well, then it was reflected at a boundary over there, the dark side of the force, and the reflected wave came back and interfered with it. So those two waves have constructive interference, the three antinodes that you see, and destructive interference, the two nodes. Here is a lower frequency stationary wave. We still see that characteristic pattern of antinode, node, antinode. There's just fewer of them. So there's a single node in between the two endpoints and places of maximum displacement or antinodes on either side of it. So this is an example of a stationary wave also. And again, a stationary wave is usually achieved when a single wave is sent out and then it reaches some boundary where it's reflected. So one way to think about it is that the Jedi wave that I'm sending out is being reflected by the dark side of the force, and we're getting a standing wave. Here you see a higher frequency stationary wave. It's characterized by nodes and antinodes. There's just more of them. So if you look closely, you could probably see places where there's no movement and then places where there's maximum displacement, the antinodes. So we can see that we can achieve a stationary wave in a slinky, but I wonder if it's possible to perhaps create a stationary wave with my favorite example wave, that of a water wave. I'll need to make sure that the force is on my side in order to achieve this. Let's go ahead and try it. I think it might be worth a shot. Release the slinky. I'm off. So as we've learned with a stationary wave, our goal is to send a wave out and let it hit some boundary where it can be reflected. In the three dimensions of the pool, it's a little bit trickier because you've got waves that are sort of going a different distance to get to this edge or to get to that edge. But if I try to match the frequency of the outgoing wave with the return wave, then indeed we could try to achieve a standing wave in three dimensions. Just like I mentioned in the slides with electrons. You know, we can think about electrons as being pinned down in three-dimensional space, and those familiar atomic orbitals that we study in chemistry, well, that's the result. Electron standing waves. Pretty awesome. So I don't know if we've got a standing wave here, but what we do got is a wave pool.